Thank you.
You can start.
Thank you, Han, for the invitation. I'm honored to give a talk in AMSS. So the title of my talk is Enhanced Dissipation for the Two-Dimensional Couette Flow. Okay, so this is a joint work with Nader and my postdoc Hui Li. So my talk has three parts. So the first I will introduce the problem, and then I will give some historical comments, what have been done, what has been done. Next thing, I will introduce our result. There are 4 results, and I will focus on the most recent result. The first one is this one is about this is the first result. We talk about the to stabilize the system. We talk about how the perturbation of the how the size of the perturbation related to the regularity of the perturbation. And the last result we will talk about optimality of the threshold. So these are the 2 results joined with my postdoc Hui Li and Li and Masmoudi. Okay, so the last piece I will talk about the idea of the talk. So we will introduce some mathematical tools we develop to attack this kind of problems. So there are this new energy estimate, which will allow us to obtain some lower bound for the semigroup estimate. And we also introduce some time-dependent Fourier multipliers and the toy model to attack these stability problems when the size of the perturbation is not small enough. Okay. So let's start. So we start from this very simple equation. So this is a 2-dimensional incompressible Navier-Stokes equation. So V here is the velocity. So it has 2 components, the horizontal component and the vertical component, because we are restrict ourselves in 2D. And the domain is in X direction is a torus. And in Y direction is the whole space. Okay, so when we set this kind of boundary, so in X direction we say this is a periodic, and in Y direction there is no boundary effect. So it's a whole space. Okay, and then here we have some a very small parameter nu. So this is a positive constant which is small. Very small, okay, and then in the 2-dimensional setting, so it's natural to introduce this vorticity, which is a curl of the V, okay, curl of the velocity, and then we can write down the equation of the vorticity, which satisfies this transport diffusion equation. So we have the transport term and we have the diffusion term. Okay, and then the velocity here, this V can be recovered by the famous Biot-Savart law. So you can introduce this psi is the stream function. So V is the gradient perp of psi, and the Laplace psi is the vorticity. Okay, so this is the basic setting of this equation, and this because in 2-dimensional case, this equation is globally well posted for the larger initial data. Okay, for larger initial larger initial data. Okay, so the problem we are interested in is a stability problem. So the object we are interested is this so-called shear flows. So shear flow is a very special type of the solution of this Navier-Stokes equation. So so when we write down this solution, we can we write down this V. It has 2 components, and the vertical component we set it 0. Okay, and then the horizontal component, we said it independent of x. So it's a time dependent and y dependent. Okay, so usually this solution, this shear flow for the Navier-Stokes equation is not a steady solution. So it means that it varies when time is moving. Okay, so it's not always independent of time. So there are only two types of steady shear flows. One is a famous Couette flow, and the other one is also famous, is a plane Poiseuille flow. Okay, so but in general, if you want to say the shear flow satisfies the Navier-Stokes equation, then this function bt of y should satisfy a heat equation. So it's a one-dimensional heat equation, but you have this small diffusion. Okay, there are some famous shear flows. For example, the Couette flow, the Poiseuille flow, okay, and also the Comoglu flow, and they both satisfy this kind of heat equation. Okay, then a natural question to ask is, are these shear flows linearly or non-linearly stable or not? Right. So I also write down this metastable. So when we say you can, let's see, we can focus on this. We can look at this Comoglu flow. So you can say when t is t is smaller than this 1 over nu, for example, then this shear flow, because this exponential part is still has some lower bound, so you can say this shear flow also affect to the system. While when t is much larger than nu minus 1, then this shear flow, you can say this is extremely small, so you can regard this shear flow also as a perturbation. So when we say the metastability, we only focus on this some finite time. So when the shear flow affect to the system. Okay. Later I will define what does this stable and what does this stability means. Okay, so it's natural to introduce the perturbation, right? Because we would like to see how this arrow changes when it goes through this system. Okay, so once we introduce the perturbation, we have we introduce this difference. So V is the solution of the Navier-Stokes equation, and then the difference between V and this shear flow, we call it U, and this U is a perturbed velocity. And also we can introduce this perturbed vorticity. So then this vorticity will satisfy the equation 1. It's slightly complicated, right, compared to the original Navier-Stokes equation. And then this U, you can also recover by the Biot-Savart law. Okay, so usually you can think about it because this U is small, right? So you can say U is of size epsilon, very small number, and then omega is of size epsilon, let's say. Then you can say, okay, the right-hand side, the non-local term will of size epsilon square. So in this way, you can say on the right-hand side is also of epsilon, but let's ignore the derivative loss. Let's just focus on the system itself. Just ignore all the derivatives. Just consider the size. Then you can say, okay, the right-hand side is much smaller than the left-hand side. So in this way, the first thing is to think about the non-local term is a perturbation of the linear system. So you can introduce the linearized equation, which we just drop the non-linear term. So we set the right-hand side to be 0. Okay, so this is a linear system. Okay, also we can introduce this linearized equation or linearized operator. Okay, so this L is time dependent. You see, because this shear flow is time dependent. Also, it has a non-local term. This you have this Laplace inverse, so it mixes the information in the whole space, right? It's not a local operator. It's a non-local operator. Okay, so so these are two difficulties, right? These are two difficulties to understand this linearized operator. The first one is time dependent. The second one is there's a non-local term. However, if you think about the flow is a very special case, which is a Couette flow. That means that the BTY, which is Y. Okay, so you can say this flow is time independent. So this T you can ignore, right? There is no time dependence. And the second thing is the second derivative of this B will be 0. So you do not have a non-local term, right? So in this case, the equation is simpler. You have this transport diffusion equation, because this you can also regard it as a transport term. So it's a transport diffusion equation under this Couette flow setting. Okay, and also you can write down the linearized equation, which you can solve it directly by taking the Fourier transform. Okay, and then you can find that omega and the psi satisfy this for these two equation, and you can evaluate these two things. You can get this is almost like a nu to the t squared. So you have a nu k square like this. So the leading order with some constant. So you can say this this one is decaying faster than the heat diffusion. Okay, and then this one we introduced a new phenomenon which we called the enhanced dissipation. So when we say enhanced dissipation, we mean that the non-zero mode, because we also set this, because this thing only happens when k is non-zero. Okay, so when k is non-zero, then the non-zero mode decay faster than the heat diffusion. Normally the heat diffusion is like this, nu t, right? Nu t. Then here is nu t cubic. So it's much faster. When t is larger, it's a decay faster. Okay, then the second thing is about the inverse damping. When we say inverse damping, you can check this part. Okay, when you can check this part, because you have this eta plus kt, and you regard this eta plus kt as some new variable c, then this eta you will replace by c minus kt square. Now you see you have a t square in the denominator. Although this will become 0, but you can obtain this result by loss derivatives. So you see, when we say the first derivative of the psi in y, then this gives you the first component of the perturbed velocity, and the second one is in x direction, so it's u2. Okay. Also, we consider the non-zero mode. Then you will find that u1 decay like 1 over t. This is independent of the viscosity, and the second component decay like 1 over t square. It's also independent of the this viscosity. So viscosity, you can set the viscosity to be 0. This damping phenomenon still holds. So this we call the inverse damping. So it's independent of viscosity. Here the projection means the non-zero mode. Okay. Okay. So then this is about the linear behavior. So a natural question is to ask is what about the nonlinear problem, right? So what about the nonlinear system? Of course, for the nonlinear system, you cannot write down the solution easily as precisely as this one, right? Okay, so it's natural to introduce this stability threshold problem. Okay, threshold problem. So the problem says that given a norm x, okay, let's try to find some constant beta. Beta may depend on the choice of this the space. Later we will talk about how this beta related to this space. Okay, and then we say that if the initial perturbation is smaller than nu to the beta. Remember, nu is small, right? So when beta is larger, the size is small. When beta is small, the size is larger. So when the initial perturbation is smaller than nu to the beta, we can prove some stability result. And if the initial perturbation is much larger than this nu to the beta, it is instability. Then we say this beta is the stability threshold. Okay, or sometimes they also refer to nu to the beta is the stability threshold. But let's think about these two things are the same. Okay. Also, there is another way to specify this kind of problem is to also introduce this nonlinear enhanced dissipation and inviscous damping, which says that given a norm the same and determine this beta. Well, when we say the stability, we say that the enhanced dissipation holds and the inviscous damping holds. Okay, so it's more precise than the previous one. The previous one just say the stability. Well, here you also need some asymptotic behavior when T getting larger. Of course, this problem is related to the second one. These two are almost the same, you can say. The second one say that given a beta, okay, the first one says that you have the space, find the beta. Now you have the beta. Let's try to find this space such that if this initial data satisfies the smallness is connected to this space and beta, then the enhanced dissipation and the inviscous damping holds. So these two are you can almost regard these two problems is the same. Okay, but it's a more precise version of the stability threshold problem. Okay, then let's review some previous work. In the two-dimensional setting, if we say that the omega to the x is smaller than nu to the beta, let's try to obtain some stability and nonlinear enhanced dissipation result. The first result is given by Bejosa, Masmoudi, and Vico. They say that if the regularity is in Jouvry space, so it's extremely smooth in Jouvry 2, then you can also set this beta to be 0. So this is the smallest beta, right? So you cannot make a beta negative because nu is positive and small. Okay, so this is the smallest one. And then later, Bejosen 1 and Bejosen Vico and Wang, they proved that if your initial data is in some Sobolev space, then if you also want to obtain some stability and enhanced dissipation result, then you need the beta to be half. Okay, to be half. Okay, then this result later was improved by Masmoudi and myself. We can weaken their regularity requirement. Indeed, we proved that in y direction we don't need any regularity assumption. So it's in L2, and in x direction we only need some logarithm regularity. So means that you can, if you write down this function space, you can say this one. Sorry. This is k, and omega initial data, right? This is k eta. This one, the L2 in k and the L2 in eta. So in this space, this is small. So only need some logarithm regularity in k. Okay, then later, also with Professor Masmoudi, we proved that if the regularity is smooth, it's much smooth. But it's also finite. It's a finite derivative, finite regularity space in Sobolev. Then we can lower down this requirement of beta. Then beta can take this 1/3. Okay, 1/3. This 40, we do not really care about this 40. We just focus on ourselves to be a finite regularity space. Later, this one can be reduced to 8, I think. Okay. Yeah. Well, Then the next one is about the finite channels setting. So you have when you have the boundary and with this non-slip boundary condition. So when we say non-slip boundary condition, means that you have a two boundary and they move, and the fluid inside of this between these two boundary move together with the boundary at the boundary. Okay, so this is the non-slip boundary. So there is no slip between the fluid and the boundary. Okay, so this is a very nice result of Chen Qi, Li Te, Wei Dongyi, and Professor Zhifei Zhang. They obtained that if X take a H1 space, and then you even with the boundary effect, you can take a beta to be half. Okay, this is about the two-dimensional case. In the three-dimensional case, the first result is also obtained by Bajorson, Pierre-Germain, and Masmoudi. They proved that if you set the perturbation in subleaf space, then you can take a beta to be 3/2. And then later this result was improved by Dong Yiwei and Zhifei Zhang. They got beta equal 1. And in the same I think during the same time, they also proved that if you set the regularity to be Jouvry space, they can reach this beta equal 1. But later, this result was the best result in 3D under this whole space setting is given by Dong Yiwei and Zhifei Zhang. They obtained the beta to be 1, and the regularity requirement is subleaf space. Okay, well, in the finite channel setting, also given by Chen Qi, Wei Dongyi, and Zhifei Zhang, they proved that if the perturbation is in subleaf space, then the stability threshold is beta equal 1. Okay, this is about the 3D case. Okay, so next I will briefly introduce what we have done precisely. The first result is with Professor Masmoudi. We proved that if the initial data is in some very lower regularity space, like this H log in X and in Y direction, we do not require any regularity. We do not require any regularity. Then, if this beta is greater than half, so you can take the equality, then this enhanced dissipation holds and the inverse damping holds. Now here I write down in a weaker form. So this enhanced dissipation I write down in L2 form. So the weaker enhanced inverse damping holds. Okay. So this is about the stability in the critical space. Also, when we so recently we want to say that this beta is optimal, right? This beta equal half is optimal. Then we realize that actually in our previous result there is a equivalent result. So it means that even here the perturbation is around the Quoite flow, while here if our perturbation is around the shear flow, while the shear flow is very close to the Quoite flow. So let's say, for example, this B minus Y, this the initial, so this B is the initial perturbation. Then the shear flow is a BTY, so which is solved by the heat equation. So if the shear flow is close to Quoite flow of the same size, nu to the half, then we can also prove that the perturbation, the nonlinear enhanced dissipation and inverse damping also holds for this kind of shear flow. So for this BTY also holds. So we only require the smallness of the shear flow. So these two results actually they are equivalent. Although this result contains the previous result, because you can set this by to by, then it satisfies the assumption automatically. So you well, in the end, these two results is the same. Okay, the next result we would like to talk about is to lower down this beta. So what will be the smallest smallest setting of this beta? So then we also we only focus on the case that we are in the finite derivative finite regularity setting. So we only focus on the Sobolev space, and we do not care about the size of the Sobolev. So H40, H100, I don't care. Okay, so then we proved that if the perturbation is due to the 1/3, okay, then the nonlinear enhanced dissipation holds, and the inverse damping holds. Okay, inverse damping holds. So this is about the stability threshold when you have a higher regularity but the larger size. Okay, then the natural question is to ask, what about when this beta is less than 1/3, right? The beta is less than 1/3, what happens? So a previous result with Li and Professor Masmoudi, we proved that if the beta is between 0 and 1/3, okay, between 0 and 1/3, then the regularity required to stabilize the system is the Jevry space. And then you have this index Jevry to the 1/s beta, and this s beta is given in this way. Okay, is given in this way. And then you can check if beta equal 1/3, then s 1/3, this is 0. So it means that this exponential to the k eta, this Jevry setting can be 0. So there is no Jevry setting. You only require some Sobolev setting. Well, if beta is 0, so means that you do not require any smallness related to the viscosity, then you only you can say the S0 is half, right? When you take a beta equals 0. So this is the first result. We also this is the first result to show the regularity and how the regularity connect to the space. And this also connect this two endpoint, right? In the previous paper, we proved that if s equals 0, then in this Sobolev setting, you need beta equal 1/3. And also in the previous paper of Nader, Bjorsen, and Vico, they proved that if you have a Jevry 2 regularity, then you can take a beta equals 0. So we connect these two endpoints and show how this regularity move together with the size. Okay. Okay, so the result is the same. You have the inverse damping and you have the enhanced dissipation. Okay, so are there any questions about the stability result?
So Weiren, I have a question. So yeah, your group available for in the endpoint case beta equal 1/3, or you just group for beta less than 1/3, and the result for beta equal 1/3 you take in your previous result.
No, actually in our in this paper we develop or we constructed this new time dependent norm that which can connect all the cases. We can do all the cases together. So when s equals 1/3, so when beta equal 1/3, you can also obtain this result by using in this paper. So we do not separate the endpoint. We do it together.
Okay, thank you. Please.
Okay, thank you. Yeah, so these three are the stability results. So you have a stability in the critical point with beta equal half, and you have a stability in the Sobolev space with beta equal 1/3, and then if beta is smaller than 1/3, you need some Jouvry space, which is given in this index. Okay, so what about so I summarize this. Okay, I summarize this result in this whole real line. So you can say the right hand side is much regular than the left hand side, and the end point is L2 setting, and then in the middle in Jouvry's in Sobolev setting, you can obtain beta equal 1/3, and in the middle you can to stabilize the system in due to the beta setting, then you need some Jouvry space, and if beta equals 0, it's Jouvry true. So this is the whole picture. Okay, then the natural thing to ask is this endpoint, this half optimal? Okay, and the next thing is this relationship, right? This beta and the Jouvry space, is this relation optimal, right? So that one requires some instability result. So let's first introduce our recent result about this instability. So this result say that, okay, if nu is small perturbation, is small viscosity, and then for any delta greater than 0, and there exists some small epsilon, and our shear flow is BTY 0, while the size, the difference between this shear flow and the Couette flow is nu to the half minus delta 0. So in the previous setting, we say that if this set is the size is nu to the half, then we can prove some enhanced dissipation and inverse damping. While here, if we just remove some delta, okay, remove some delta, so make this size slightly larger, our result is a nonlinear enhanced dissipation fail. Okay, the nonlinear enhanced dissipation fail. Also the linear one. So of course, when the nonlinear fails, the linear also fails. Okay, so so this is our result. So more precisely, let's give a more precise version of this result. The first thing is so when you want to prove some instability, it means that you need to find some initial perturbation which does not satisfy the previous regularity or size assumption, and then you can find some instability in this solution. So our result is given by, you can always find some initial data, and this initial data is mean 0, so there's no 0 mode, and then the solution solve the linear system has some lower bound. Okay, has some lower bound. You have some exponential growth. Okay, you have some small constant C here, and this is exponential growth, and you have some nu to the, and you can say that this time t, this capital T, this time is greater than this number, 1 over this number. So it means that we obtain this exponential growth above the time, so it's more than the 1 over. So you can say that if you have some system grows like exponential lambda t, if your time is just 1 over lambda, it's nothing. You do not do anything, right? Because you just say, okay, it's bounded. It's bounded. It gives some fine growth, only a little bit growth. Well, if you can extend your time to be 1 over lambda log 1 over lambda, lambda is small parameter, then it become larger, right? This become larger. It's become 1 over lambda to the epsilon, in some sense. Okay, then okay, this is about the linear result, and for the nonlinear result, it's the same. You have the nonlinear system, and we also set some initial regularity and size assumption on the non-zero mode, and we can also obtain some lower bound of this solution. Okay, and in particular, if you take the end point, the time, the largest time, which our estimate valid, you will find that this the L2 norm of the perturbation, the L2 norm of the perturbation is of this size, c to the nu to the c epsilon 1. So it means that this when this nu is extremely small, then it grows much larger than the initial data. Okay, so that's our instability result. Okay, so let's say so I still have time. Okay, so this is a whole picture I draw here about the result of this stability and the instability. So we focus on this case, so omega in Jouvry setting, and then you can say that if the index x s sigma and the beta is larger, means s larger or sigma larger means the perturbation is smoother, has more regularities, and if beta is larger means that the size of the perturbation is smaller. Okay, so usually these three things, when these three are larger, you can have stability and enhanced dissipation. Okay, and then we now the existence result is given by the stability is in this red line. So beta equal half, then you require some you do not really require any regularity in S and sigma. Okay, you can take S be 0 and sigma be 0. And if beta is 1/3, then you require this sigma to be 8. In our previous result, we can lower down this sigma to be 8. Okay, and then if you require some perturbation which is larger than u to the 1/3, then you need some Jouvry regularity, and this Jouvry S Jouvry 1/s, this S is related to this beta. So you get this red line again. So usually the right hand side part and the above part of this red line, it is stable and it has enhanced dissipation. Okay, and then the blue line, the green line gives the instability result when sigma equals 0 and the beta equals half is the optimal, right? Beta equal half is optimal. When beta is slightly smaller than half, you have some instability result. Okay, so you can almost see this gap. So you have this gap, this area, how these two red lines connect to each other. This is open, and also this area. Whether you have this instability result or stability result is also unknown. Also, there is one curve, this one, when S equal half and beta equals 0, for the Euler equation, when nu equals 0, there is an instability result given by Deng Yu and Professor Masmoudi. They proved the instability result. So I also dropped this curve here. So yeah, so these are all the results we have. Okay, so let's make some comments about our instability result. Then we move to the idea of the proof. The first result is about the first remark is about the size, the constant. So in our previous result, we obtained that this omega t in L2 at time t is greater than 1/nu to the c epsilon 1 of the initial data. So when we say this C and this epsilon is independent of nu, and the nu is a very small constant. So this gives you a very large amplification, so which gives you the instability, and which also say that the enhanced dissipation fails, right? Enhanced dissipation fails. Okay, then the second remark is say that actually in a very old paper, Gill gives a very formal discussion about the instability of shear flow By0, and he say that if the shear flow of this form, then he point out that if the shear flow is to become a turbulence, means that it's become instability, it become unstable, then gamma cubic divided by nu must necessarily be larger. Okay, in our setting, our gamma is nu to the 1/3 minus delta. Okay, this is our gamma, and you can say that actually our result matches very well with his observation. Okay, and then also he also mentioned that the time which the growth can be measured is of gamma minus 1 log gamma minus 1. This is the same time as we proved in our paper. Okay, then this is a second remark. Okay, the third remark is about the L2 norms, because our instability happens for the L2 norms. Well, for the Quoite flow, you have this very good transport diffusion equation. So when you take the L2 norms and the integration by part, actually you proved that this L2 norm square plus we do not care about the regularity. We always think about our data is in Gervais space, but we in some Schwarz space, but we measure in L2. Okay, we measure it in L2. So this one gradient omega nu L2 square. This is equal to omega initial data L2 space, right? So you have this identity. So which means that in L2 setting, you are always stable. Well, the question here is asking about what about the enhanced dissipation, nonlinear enhanced dissipation. Okay, so here we only focus on the non-zero mode. Okay, so we can say that actually our instability tells you that the information of the zero frequency move to the non-zero frequency and make the non-zero frequency become larger, and the time is in some sense optimal. Okay, in some sense optimal up to a constant. Okay, the last comments is about an application of our method to the ideal fluid. So for the Euler equation, okay. So we obtain that if the shear flow is very close to the Quoite flow of this size, gamma is small parameter, and then we can also obtain this exponential growth, which also means that you have an eigenvalue which whose imaginary part is of this gamma this size. So this is also give a quantitatively a result of the semigroup estimate of the Euler equation, linearized Euler equation. Okay, so now let's move to the main idea of the proof. Okay, so in the previous paper, we linearized around the Quoite flow. So let's say I write down in a vorticity form. So the -1 is the vorticity of the Quoite flow. So this is the vorticity of the Quoite flow. And then we linearize around the -1. Then we obtain the equation of omega. Well, now you can say that if our perturbation is slightly larger, okay, slightly larger, then you can say when we still linearize around this -1, it's not accurate anymore. So the idea is to say that instead of linearizing around the -1, we linearize around the -1 plus something, okay, plus something. So here we just choose this Gaussian equation, Gaussian function. It's a Gaussian type function. It's exponential new to the y square, this Gaussian function. And you can check that this L2 norm of this Gaussian function is a gamma half, a gamma square divided by gamma to the half. So it's almost like a gamma to the 3/2. Okay, 3/2. This is gamma is small. Gamma is small. Gamma is like new to the 1/3 minus 2/3 delta 0. So this means this is like a new to the 1/2 minus delta 0. Okay, so you can say this omega gamma is still a very small perturbation, but we have to take this omega gamma into account when we want to say some instability. So this we call the secondary linearization. So instead of linearize around the Quoite flow, we need to linearize around the Quoite flow plus something. Okay, and this thing is small. Okay, then once we write, we introduce this new shear flow or new background flow, and then we can linearize around this flow, and we obtain a slightly complicated system. Now you have this non-local term, right? This is a non-local term, and then to observe some instability, then we can simplify this model. And the first simplification is also the same. You drop the nonlinear term, right? Because we think about the nonlinear term does not affect. And the second one is we drop this uy partial u partial x omega. Why we drop this? Because this is extremely small. It's a gamma square. Okay, in the previous, we say this is a gamma to the 3/2. So this is even smaller than the previous set size. So we also drop this term. Okay, we also drop this term. So we end up with this linearized equation, and we can say that it's still time dependent because this flow is time dependent. So we end up with a linearized equation, linearized system, which is the linearized operator is time dependent. Okay, so we would like to prove the instability. A natural way to study this is to find some glowing mode. So it means you have some glowing eigenvalue, right? With for example, the C is an eigenvalue of this operator, and you prove that the real part of C is positive, then you can find this exponential growth. However, here the one disadvantage of this operator is that it's time dependent. So it's a very unlikely for you to use this eigenvalue argument to solve this instability problem. The second thing is that actually this operator has no spectrum. So it's a so you cannot find any glowing mode for this problem. Even the spectrum, you cannot find it. So you can formally think about this operator behaves like the area operator, and then as y goes to infinity. And for this area operator in the whole space setting, you cannot find any eigenvalues or spectrum. So this is two difficulties we need to overcome. Okay, the next thing is to introduce this change of coordinate, because you have this, we have this y partial x term, so we introduce this change of coordinate to absorb this term, and then we write down in a Fourier transform after the Fourier transform in both x and y, and then we end up with this system. Okay, now the previous product become a convolution here, and then easy calculation shows that actually the Fourier L1 L infinity space of this F has this enhanced dissipation. You can see you have exponential c nu t cubic. So this also implies that this operator itself has no spectrum. Okay, so you cannot use the eigenvalue argument to obtain the instability of this problem. Of course, you can also write down the L2 norms, which also has this enhanced dissipation. So I take the minimum, okay, minimum. So when t is larger, this term dominates every term. Okay, okay. Then the next thing is to choose a good initial data, because our goal is to say there is some initial data which gives you the exponential growth, right? So we need to describe some good initial data. So the first thing is that, okay, we only focus on the mode 1, okay, mode 1, so k equal 1. So our initial data has only one mode, so it's a cosine z, okay, and then also in order to make this f function in y is a real function, we also require some even or symmetric assumption of this function. Okay, then we can write down the equation of linearized equation of mode 1 and -1, and a simple observation gives you that of the -1 mode, if you take a minus sign, it enjoys the same equation of the mode 1. So you only need to estimate one equation instead of two. Okay, so this is the one thing. Okay, the second thing is that we in order to make this function real, so we need some even assumption of the initial initial data, but that's fine, right? That's fine. So we have this freedom. Okay, and then again the same thing. Even we restrict ourselves to be mode 1. We also have this enhanced dissipation for the solution. So we would like to say that the exponential happens when this term can be negligible. So the time should be slightly before nu to the -1/3, right? The time, because when time is greater than nu to the -1/3, this term dominates. This exponential t to the cubic will eat this exponential growth. So we cannot exceed that time. We should focus on ourselves to be a finite time problem. Okay, so all these kind of things actually tells us that we need to introduce a new method to obtain this lower bound. So here we use this energy method. Okay, we use this energy method. Okay, so several observations to gives you the growth to tell you the growth mechanism. The first thing is that our time is this time. So gamma -1 log gamma -1. This is our time, because before this time, gamma -1, we cannot see any growth. Larger than nu to the -1/3, there's no there's the enhanced dissipation effect. So we only focus on ourselves in this very small narrow piece of time. So our time is from 0 to gamma -1 log gamma -1. And then the first thing is that you will find that the diffusion term actually does not contribute to the system. Okay, this is the first thing. The second thing is that the rapid growth happens when eta is close to t and Kc is greater than eta. Kc minus eta is like gamma -1. Why is that? You can check this toy model, and you will find that when this eta close to t, the denominator become small, so it gives you the largest coefficient. And then when c greater than eta, then it gives you all this the function multiplied by g1 is a positive, so it gives you a positive force. Okay, and then when c minus eta is like gamma minus 1, so means that this function actually take its local maximal. This function vanishes at 0 and decay exponential faster, double exponential faster at infinity. So it has some maximum point like as at a gamma around the gamma minus 1. So we just focus on this regime. Okay, and then the next thing is that a smaller positive regime, right? So this eta close to t, this smaller positive regime will talk to a larger regime, right? This gamma minus 1, that's a larger regime. So the small region talk to larger region and gives its growth. Okay, so the last thing is our choice of the initial data. So we initially set all the data to be 1 in this regime, because C is smaller than this time of the same time as our largest time, and then we set that the G will be 0 if the C is larger than this complex. So it means that we set this G1 is it has some complex pointers. So we use a computer to obtain some picture of this glows. You can see this dot. The dot is like C equal T. So C equal T. So in this around this dot, you will find that this dot glows exponentially. So how to justify this? So in order to justify this, we introduce this. We separate this frequency into several regimes. The first regime is the excitation regime, which we say that this regime, when eta in this regime will excite the regime next, which we call the growth regime, the region of growth, which make this region of growth, the data, the information become larger. Well, the last regime is the waiting regime. It's a way to become a growth regime. So it's waiting for growth. Okay, and then we set ourselves into this 4 regimes. The rest part we do not give a name, so there are 4 regimes. Okay, there are 4 regimes, and then in each regime we prove the key lemmas. First, in the excitation regime, we say that the data during this time does not change too much. So it's almost like the time in the previous step. Okay, in the region of growth, we prove that the data has some positive growth. It becomes larger, excited by the exciting regime. Okay, and in the waiting regime, we prove that it is the data still have some lower bound, right? Initially we said that the data is like 1. While in the waiting regime, we prove that it still has some lower bound. It's almost close to 1. Okay, and then the last lemma tells you that with our well-chosen initial data, the assumptions of this lemma holds automatically. Okay, yeah. So this is a final growth mechanism. So I would like to introduce in a formal way. So the first thing, at time equals 0, all the data is 1. Okay, all the data are 1. Okay, the next step is to say, okay, this time, this is our initial time. This time is in the excitation regime. Okay, it is in the excitation regime. It will talk to the next two. Okay, it will talk to this regime, it's a closed regime. Also talk to this regime, it is a closed regime, and make the waiting regime. We also formally set it to be 1. Okay, then what do we have? We have that this regime plus this the information from the excitation regime, it become 2. And the next excitation regime also plus this 1 become 2. Okay, the next step, the time become a gamma minus 1, and then this 2 become an excitation regime, right? The time is forward, so the Cassie is moving along the time. So the time is moving to this is a t equal gamma minus 1. Time is moved to this frequency, and then this 2 will talk to the next 2 regime. Okay, we'll talk to the next 2 regime and make this 2 become 4 and make this 1 become 3, right? 1 plus 2 becomes 3. Okay, then the rest part we also think about this in the waiting regime, it still be 1. Although it's a 1 minus something, but we do not care. Okay, the next thing, the time now is become a 2 gamma minus 1, and then this 4 will become an excitation regime, and it will talk to the next 2 regimes. Okay, talk to 3 and talk to 1, and then this 3 becomes 7, and this 1 become 5. Okay, and so on. This 7 become excitation regime, it's talk to 5 and talk to 1, and this 5 become 12, this 1 becomes 8. And in the end, you will find that when you connect this, when you connect all these, when you connect all these lines, we will find that this is a Fibonacci sequence. So Fibonacci sequence has an exponential growth. So that's how we prove the exponential growth. Well, this is a point. It seems a pointwise, right? It seems a pointwise. Actually, the size of this regime is of gamma minus 1. So actually, we prove in this gamma minus 1 regime, all the data grows this exponentially, pointwise. So in the end, actually, we proved that the data has some exponential growth till the time gamma minus 1 log gamma. Okay, so I would like to stop here. Thank you.